Okay, so yeah, I was going to talk about ODE solvers as Bayesian state estimation. So there's a plan here, I think. So there's 3 points. An ODE, what is that? How do you solve it? I'm not going to talk too much about that, but I'm kind of going to sort of sketch out the general idea. And then I'm going to talk a lot about Bayesian state estimation. So hopefully a lot of people don't know about Bayesian state estimation. How many have heard about it? Hands up. Okay, so a bit less than half, so probably it's not a totally shit plan yet. And then, once we know Bayesian state estimation, then it turns out that sort of framing this solution of ODE solvers as Bayesian state estimation is fairly simple, and we can just use standard algorithms from this sort of Bayesian state estimation to make things work. And then, if time permits, I might also talk about a bit on how you sort of prove properties of these solvers. We'll see. So yeah, let's get into it. So what's the differential equation? Well, John told you what a partial differential equation is yesterday, and he did it very well, very elaborately. I'm not going to do that. I'm just going to say there's this function y, and there's this dot over it, which means it's the derivative of y. And if it equals some function evaluated at y itself, then we have a differential equation. And again, it's not sort of uniquely solvable unless we impose some sort of constraints. Typically, we post initial values. So we say y naught equals zeta. And we might also be proper and say that we consider the equation on the interval 0 to big T. And now you can sort of formally solve this by just taking derivatives on left-hand and right-hand side. And so then you get a Taylor series expansion of the solution. But this is very practical. So what do you do in general? Did I go to both? Yeah. Yeah, so you can integrate both sides and turn it into an integral equation instead. So this is the same as before. You just put integrals on both sides. And now we have sort of this self-referential integral. However, what's important with ODEs is that we can sort of split this integral up. So I can first integrate from 0 to s, and then from s to t, where s is some intermediate value between 0 and t. And so then this bit is just the solution at y at s, and then we have an extra bit. And so then, yeah, that's just this guy. And if we call this guy just phi of ts, whereas it's typically called a flow map from s to t. And it sort of encodes all information we need to go from one point to another point over some interval. And typically, how standard integrators are designed is then to consider some solution grids. So we take a collection of grid points Tm, and then, well, we just get this recursive structure of the solution. So we just evaluate this flow map at the previous point to get the next point. And there's no numerics yet. So typically this flow map then is of course retractable, and that's the only thing we need to approximate. And again, that's just saying that we need to approximate this integral basically. And it turns out if the adjacent time points are kind of close together, then we have an integral over a very short interval, and they're very easy to approximate. So, for instance, you can just plug in y at the left-hand endpoint, and then just say, pretend that v of y is constant with that value. And so then it's just the integral of a constant, and now we get what's known as explicit Euler. And I'm not going to go into more elaborate schemes, but typically this is how people do it. They sort of frame it as a quadrature problem, though the problem is that the integral is self-referential, so you don't really know what nodes to put in there, so you sort of do some kind of extrapolation scheme, and then you make sure that the extrapolation scheme is faithful to the sort of Taylor series expansion of the solution I showed you earlier. And so that's how you do it. And John told you how to solve PDEs yesterday, and you can sort of, well, if you just exchange the dot for a partial t, we have a PDE, and so we can solve it. And this is how we do it. So what I write down here is, so we have a differential prior over the solution y, but we also need its derivative, because our data is derivatives. So let's just say we have a GP over y and its derivative. And then we have some initial data. So, well, theta was our initial condition. And we can also add the initial condition for the derivative, which is just v of the theta per definition. And then our data is basically just that our derivative minus our vector field evaluated at the solution should be equal to 0 on our grid. And, well, this is just nonlinear GP regression without noise. And so we can sort of just write it out, and for instance, you can do some kind of maximum a posteriori approximation. So here we just have the prior, or well, the log prior, removing all the terms we don't care about in that likelihood, like the determinant, it's constant with respect to x and so on. And then we have this constraint here, right? And so we can solve this, for instance, with Gauss-Newton or something like that. And it works. However, we are not done 5 minutes into the presentation. The problem here is that, as people have been talking about, we need to compute inverses or, well, solves with respect to this gram matrix K. And this gram matrix K is of order n cubed, quadratic n, what is n square? N square elements, which means solves are n cubed, which means it's very expensive. The linear algebra people have been talking about how to sort of approximately solve systems. I'm going to take a different approach to change the model in a way that it sort of inference becomes cheap automatically. And roughly speaking, that means we have some kind of stochastic process prior that sort of mimics this sort of recursive structure of the solution of the ODE. That's obtained by, yeah, oh, no, I did not have an illustration there. So that's accomplished with Markov processes. And so what's a Markov process? Well, so suppose we have a stochastic process X. A Markov property then just says if we have the process at some time point t, and we have the process, or well, we don't have that, but suppose we have the process at a bunch of time points t1 through n are known, and then at some future time point t, what the conditional density then just depends on the latest time point. That's what this is saying. So we don't actually need to record the entire path of the process to know how to predict it in the future. We just need to know the sort of latest value. And then I'm going to denote this conditional density by f, and maybe call it a transition density or Markov kernel or something like that. And of course, you can just use this property then to sort of factorize any sort of finite dimensional distribution. So first you use this sort of like, oh, we could take x and condition on everything else, and then we take the joint of everything else, and then condition of everything else just becomes this forward kernel. And well, then we just keep everything else, but we can keep on factorizing this one with respect to, so we take xn minus 1 condition on everything else, and so on and so forth. And so then we just see this. So we need an initial density, and then we just need a these sorts of forward transition densities. And so it's a very complex representation. And it has this sort of recursive structure, as you see. And yeah, so if you're familiar with graphical model, this is the graphical model for a Markov process. So it's very simple. It's just a line. And then, of course, there is this sort of like famous saying that, or well, that Markov process has the property that the future and the past are conditionally independent given the present. And what that means is, so if we have some 3 adjacent time points, tn minus 1 to tn plus 1, and we condition on the current one, then there's sort of conditional distribution factorizes, which is just the definition of independence. So that basically means if we know this guy, what happens here and what happens here, they don't communicate with each other, so we can sort of treat them separately. And so a very useful instance of Markov processes on Gauss Markov processes. And there we just specify the initial condition to be a Gaussian distribution with some mean mu naught and covariance sigma naught. And well, our transition densities are then just Gaussian. So we could have some matrix times x to be the conditional mean. We can add some constant vector as well, and then we have some sort of transition covariance q. And these sorts of processes can sort of be thought of as arising from the linear stochastic differential equations. And that's just saying that a little increment in x corresponds to a times x times a little increment in t plus b times a little increment in w, which is going to be a linear process. So a continuous time random walk that is Gaussian. And in that case, the transition parameters are just given by matrix exponentials for this transition matrix, and then you have this sort of controllability Gramian is what they typically call it for this transition covariance. Now we've just talked sort of about the prior, so if we're going to do estimation, we need some sort of measurement of it. And that typically just means that we measure each state at each time point, maybe. We can skip some time points, but typically we have a measurement corresponding to each time point. And so that's this graphical model. X and Y are kind of jointly Markov, but with even more restricted sort of structure. So we can still use all our Markov shenanigans to sort of understand these models. And that means we can just write it down like so. So we just need to specify an initial condition for the state, the transition density for the state, and then we just need some measurement model for the state in case a state is measured at some particular point in time. And I call this measurement thing G2. And so the estimation problem then is, given observations Y on some grid T1 through N of our Markov process X, we want to estimate it. And we want to do it in a Bayesian way. Well, I'm going to do it in a Bayesian way at least. And so we know Bayes' theorem, you take the prior and just multiply the likelihood and so on. But now let's examine how does the prior look like. So the prior likelihood, well, we saw it's a Markov process and we saw its joint density. Just this multiplication of transition densities times initial density. And we see that it has this recursive structure. So the joint density up to k is equal to the joint density up to k minus 1 times transition density k minus 1 to k. That's the Markov property. And our likelihood of the path up to k is then just the product of all this g up to k. And it also has this sort of Markovian structure then. So that's just the likelihood of the path up to k minus 1 multiplied by the latest g. That is k. And then we also have this sort of marginal likelihood, which we need to normalize the posterior, and that's just likelihood times prior, and then you integrate. So how does this work then? Well, so the posterior is, I'm going to call it gamma. It's just equal to, well, likelihood prior divided by marginal likelihood. And it has, again, this sort of recursive structure. So we can take away the sort of latest things from the prior and the likelihood. And then we have, well, something that is proportional to the posterior over the path to k minus 1. And then we have, well, latest likelihood and latest transition, and then marginal likelihood of something that is up to k. Now we can multiply this and divide by the marginal likelihood of up to k minus 1. And then this guy turns into the posterior over the path up to k minus 1. And then we just have this fraction of marginal likelihoods, and then these kinds of, well, the latest transition and measurement density. And this fraction of marginal likelihoods is, of course, just by Bayes' theorem, the sort of one step ahead prediction of the measurements. The reciprocal of it. So it's 1 over y, m of yk given y1 for k minus 1. And now if we sort of, we need to develop a kind of recursion for this marginal likelihood if we want to sort of form the posterior in this recursive fashion. So, how does this work? So we take the definition of marginal likelihood of the path up to k, and then we get, and so that's just the definition of this integral, and then we just divide by the marginal likelihood up to k minus 1 on both sides. So we have this guy there now. And then we just use the recursive structure of this path likelihood and the prior density. And then we absorb the marginal likelihood up to k minus 1 to get the posterior of the path up to k minus 1 times these things. So that kind of simplifies a lot. We can do things go even further. I'm going to define the filtering density at time k minus 1 as this sort of marginal density of x at tk minus 1 given all the measurements up to tk minus 1. And then I'm also going to define the prediction density at time k, or one step ahead prediction density. And that's just going to be the marginal density at tk of the state x, given all the measurements up to but excluding the present time point. And that's by the Markov property is this guy. So we can, so this is the filtering density, and then we just use our transition density, integrate it to get the prediction. Again, Markov property. And now we can look at the marginal likelihood recursion again. So this is what we had before. We integrate out everything up to k minus 2. And so then we just get the sort of filtering marginal at k minus 1 here instead of this sort of entire path. And now we can also integrate away k minus 1. Now we get the prediction density integrated against the sort of current likelihood. And so we have this recursion. So if we, so we have, our posterior has a recursive structure, but we need have to have a recursive structure of the marginal likelihood to sort of complete the recursion. and in order to complete the recursion for the marginal likelihood, well, we're going to need a recursion for this sort of filtering and prediction densities. But that we kind of have that now. Yeah, so essentially the result is as such. What we do is we take our filtering density at k-1, and then we form the one-step ahead prediction by just integrating against the transition density, and then we get the marginal likelihood increment by just integrating the one-step ahead prediction density against this g at current time. And the filter update is then just proportional to this prediction density times likelihood, where the constant of proportionality is the reciprocal of this guy, of course. Because if you divide by this guy, you get 1 equals something. So what happened? Well, I wanted sort of a recursive construction of the posterior. We kind of have that now, but we also got a recursive computation of the marginal likelihood in the process. And we got this so-called filtering density. And recall that's just the marginal at the current time given all the measurements up to current time. So in a sense, it's sort of our best guess of the present, which is kind of cool. However, we might want a more useful representation of the posterior, and maybe also be able to compute posterior marginals, or well, probably you do want that. And that just corresponds to taking an entire measurement sequence at t1 through n, where n, and then just looking at the marginals at tk for tk less than tn. So let's look at a backward recursion for the posterior marginals, because by definition, the terminal filtering density is the posterior marginal at the terminal time, because then it's conditioning on all the measurements at that time. So since we have the sort of solution at the endpoint, we might want to sort of see if we can go backwards again to get the solution everywhere else. So first we go forward and accumulate information, and then we realize that we have a lot of information over here that we didn't have over here, so we need to go backwards again. And how do we do this? Well, by definition, the posterior marginal at tk is just the conditional marginal at tk given all the future states and all the measurements times the marginal of all the future states given all the measurements, and then you just integrate them out. Now, the Markov property actually implies that the posterior also has a Markov property, and it's even has this sort of backwards Markov property. So if I look at conditional density at xk given all the future states and all the measurements, that's just equal to the conditional density of xk given xk plus 1 and all the measurements. And so a consequence of this is that we can sort of construct these marginals by just taking our smoothing estimate at the one step ahead in the future, integrate it against this sort of backwards transition density to get our next marginal. And the way you see this is, again, this sort of conditional independence assumption. So if I know x here, then everything, then it sort of gives me everything I need to know xtl because from the right, because this guy and these guys are then irrelevant due to this sort of conditional independence property of Markov processes. And so I'm going to call this sort of backward transition density B, and then I'm going to use Bayes' rule to sort of get a more suitable expression for it, keeping in mind this conditional independence assumption. So this is just Bayes' rule. So this is kind of, let's see here. Yeah. So this is just the joint density, and then this is just the marginal density, and I divide by that. But this thing, so this is the one step ahead. Prediction, given xk, but that's just the filtering marginal of k times the transition density. So that's how this thing simplifies. Yeah. And then I just divide by the one step ahead prediction. And so this is just base theorem. And so now this backward density just depends on the filtering density, the prediction density, and the transition density. And we have recursions for these. And so that was sort of rather sort of just formally manipulating a bunch of transition densities and so on. Now let's see what happens more in practice where we can sort of implement things. And again, we go back to the beloved Gaussian case. So we have, again, in this case, our sort of partially observed macro process looks like so. So we have initial distribution on x, and then with transition densities for x, of course. And then we have a Gaussian measurement of the state as well. Now, because Gaussian models note that in all the sort of manipulation of densities and so on I did before, I only did marginalization and I did conditioning or base rule. And Gaussian models are closed under all of these things, which means that all of the things I care about are going to be Gaussian. And so, in order to look at what happens in the filtering case, I'm just going to denote the prediction density by, well, some normal with a mean mu, and then a time point evaluated time point, and then a sigma evaluated time point. But I'm going to use a superscript minus to indicate that we're not using any measurements at that time point yet. And for the filtering density, I use the same notation, but I removed the minus to indicate that I did in fact accumulate the measurement. And our sort of marginal likelihood increments are also going to be Gaussian, and I'm just going to call the mean y hat and the covariance s or something. And I'm not going to sort of go through all the algebra to sort of realize this, but once you do that, you arrive at the sort of famous Kalman filter. So that's just a recursion for the mean and covariance, and so you take the previous filtering mean and covariance, and then you sort of shoot them through the transition density, and that looks like so. So you take the mean multiplied by transition density to get the prediction, and then you have to do some after product things with the covariance. And the update again here, this is just Gaussian conditioning. You're all familiar with it, so S is just my measurement covariance, marginal measurement covariance, and then I call this K matrix, the sort of gain matrix, which sort of corrects my mean estimate given the measurement like or well, the measurement error even. And then you have this sort of down date for the covariance. And now what's left for the smoothing stuff? Well, some notation. So the backwards kernel, well, it's going to have at least some affine map A that depends on xk plus 1, and then I'm just going to call the covariance there P, and for the smoothing state or the posterior marginals, I'm going to call the mean psi and the covariance lambda. And again, you just do all the algebra, it's completely analogous. And so the backward kernel, again, this was just an application of base rule. So I'm just going to call the gain matrix G here in this case. It's kind of the same as the update in the previous slide with different parameters. And then this conditional mean function is then just filter mean plus gain times x minus prediction mean at the next time point. And well, this P is again just a down date of the filtering covariance. And so then we just get this backward recursion, because recall posterior marginals, you just marginalize backwards step by step. And what happens is, well, you replace the x with the smoothing mean at the time point one step in the future, and then you also get this other product, which the sort of transition matrix, which is going to be G here in this case, with the previous or future, the future covariance, and then you just add this P from the transition kernel. Okay. So back to Bayesian ODE solvers. Hopefully we have some sort of idea of why Markov processes are amazing, and we can do quick inference in them, because since everything is recursive in inference, it's going to be linear in type. So again, we have this vector field V. We have the same differential equation as read before. And now I'm apparently calling the actual solution of the differential equation y dagger. And so that's what we're trying to solve, but now we have the problem of what prior should we choose. The likelihood, or well, the data is kind of semi-fixed. You can do some things with it, but typically it's quite good to sort of just say, please solve my differential equation at these points at least, or look to be solving it. But anyway, so for the prior, I'm going to use one of these sort of stochastic differential equations. So my state is going to be x, and it's going to solve this linear differential equation. I'm going to add some square root of kappa here, which is going to be some sort of parameter I can sort of turn around and to sort of calibrate my model. And then in order for this to actually make sense as a model, I need to say that there are matrices EM such that when I multiply by x, I get the nth derivative of y. So if I multiply by E naught, I get just y, and then I have successive derivatives up to some order nu. Now, for our sort of initial state, I'm just going to say x is equal to x naught dagger, and I'm going to say this is the correct x naught dagger in a sense. So in a sense, this is just a model of all the derivatives of y, and so what this basically means is that EM of x naught dagger is equal to the nth derivative of the tree solution, and apparently this makes sense because we can sort of get this kind of cheaply by auto differentiation. And here are some assumptions I'm not sure I'm going to necessarily need, but they're sort of related to the reproducing kernel Hilbert space structure of the prior. And so controllability basically just means I can replace this Wiener process by any function, and then I can design this function to bring the state to anywhere I want in finite time. In fact, within any kind of time interval I want as well. And observability basically just means that I can reconstruct my entire state x by just observing y. Which basically means I can sort of map back and forth between x and y. And again, we'll discuss Markov property. So we have this transition densities, and we have the transition matrix and the transition covariance. Same as before, I used this kappa in front here, which is to be decided. And so this was a fairly general sort of structure of the model. So what do we do in practice? Well, there are some simpler cases which we can look at. So one option is to just say my nth derivative, which is the last derivative I was modeling, is just equal to square root of kappa times a Wiener process. And if you work things out here, this corresponds to a model of y, where you first have a new order Taylor series expansion, and then you have plus some integral here, and this is basically sort of Taylor's remainder theorem in integral form, except we've replaced the actual remainder term in the integral with a stochastic term. So we're modeling the remainder stochastically. So in that sense, it seems like a reasonable model, maybe. However, another option is if you know more structure in your problem, so say, for instance, our vector field B is semi-linear. And what do I mean by this? Well, I mean that it has a linear bit, L times y, plus a non-linear bit, N of y. Well, what can I do then? If I sort of formally differentiate this new times, then I get that, well, then I get, well, basically the same thing in the linear bit, and then I get a new root of n. And then if I sort of formally approximate this non-linear bit with a white noise term, then this corresponds to this sort of integrated Orstein-Uhlenbeck prior, which I call it. So we keep the linear bit, and then this non-linear bit is just noise. So this is particularly good if, like, all the fast dynamics in the solution are determined by the linear bit. Because then we have that already in the prior study. Hopefully we get better solvers this way. And so this is sort of how the priors might look. So in the top row we have integrated Wiener processes for derivatives 1 through 3, and on the bottom row we have this integrated Orstein-Uhlenbeck processes for these sort of semi-linear problems with the same number of derivatives. And so the integrated Wiener processes are kind of boring. You see that the paths seem to grow a lot, or the variance seem to grow a lot. Whereas these sort of integrated Orstein-Uhlenbeck processes can have a lot more structures. So, for instance, oscillations, but also growing variances. Particularly, you might see that in this one. Now, these are our priors. Do we think any of these realizations actually solve an ODE that we're interested in? Probably not. So, in practice, our data is going to do a lot of the work for us. Now, so the inference problem can now be cast like so. So we just, well, we have our transition densities. We don't need the initial density because we know the initial states, as I mentioned before. And, well, our likelihood is a bit weird because, well, it's just essentially a constraint on our solution at the time points. So we want the derivative to equal the vector field. But formally, we can think of this as a likelihood of G where we observe 0 according to this non-linear measurement model now. So now this is not a linear Gaussian model. And we also have 0 variance. So this is just the way. You can also think of this as a sort of Dirac likelihood. Now, we almost know how to do this. So, well, we have the formal sort of Bayesian state estimation recursions. We have the Gauss-Markov, this corresponding recursion to Gauss-Markov models, but then we assumed that everything here was linear. So what do we do when things are nonlinear? Well, we pretend it's linear. So there's different ways of pretending it's linear because our measurement model has this linear bit and non-linear bit. So we have the derivative minus vector field, which is possibly nonlinear. So we can just, the first best approach would then just be to, well, let's do the least effort possible and then just approximate the nonlinear bit with a 0th order Taylor series. So we approximate V of E0x by just replacing x with the predicted mean from our filtering recursion. So we can always predict, and then we can't do base update until we linearize our model. So we linearize our model like so, and now we can do base update, which means we can do the filtering recursion, and the smoothing recursion has no problems because there's no non-linearities there. Now the second approach is, of course, to do a first order Taylor series expansion of the vector field. So what happens then is that rather than just having an observation matrix that is equal to E1, that is to say, we observe the derivative, we have something more complicated, which is a linear combination of the derivative and the sort of solution. And then going back to sort of the formal sketch of the solver I showed you earlier with these ground matrices, we can also just consider computing in maximum a posteriori solutions. So this is just a sort of log likelihood of the prior rescaled and probably sign flipped and so on. And then again we have these constraints that we want our process to sort of hit this sort of correct curves in the state space so that it looks like it solves the differential equation. Now, since we linearize everything, we can just run these linear things. And the marginal likelihood kind of just decomposes according to this guy. So these are then just the one-step prediction. That's this, which is just, if you take the product of these, you get the marginal likelihood, and if you take the log, then you get the telescoping sum, and then you get this. Now, all of our covariance matrices now depend on some parameter kappa, which is from the model. Recall I scale the noise by square root of kappa. Now one can show that sort of all the covariance matrices in our recursion depend on kappa like so. So there is some constant matrix times kappa, which makes this sort of marginal likelihood in terms of kappa very easy to deal with, and we can maximize it. And so we can actually find a kappa hat that looks like so. So these are kind of our measurement predictions. Then we just whiten them with our measurement covariance, and then we just take this Tronarp and sum them up and take the average. So we can do inference, we can calibrate, which means I might have plots. Yes. So now if we actually implement the color filter recursions and so on, for some problem, it might look like this. So I'm not going to show you what particular problem. I'm just going to sort of show you two different priors. So red is the integrated Wiener process prior, which just didn't incorporate any information about the solution. And then we have the green one, which is the integrated Ornstein-Uhlenbeck process, which included linear bits. And so you see, the prior kind of matters a lot in terms of what kind of solution you might get. And now the correct solution is in fact plotted here in black. I'm not sure how visible it is, but it's kind of almost in the middle of these sort of credible intervals for the integrated Ornstein-Uhlenbeck process. And so what we can deduce from this that the prior kind of matters a lot. So the IVP is not too bad in this case in the sense that it's at least covering the area of the true solution. It's just way too unnecessarily uncertain, let's say. So I guess Nathaniel is going to show you how to actually make plots like these later. Okay, maybe. We'll see. Now there are of course some sort of theoretical properties of solvers that people typically care about in numerical analysis. So one property is sort of stability. We don't want our solver to just blow up for no reason whatsoever. That's a bad sign. And we might also want some sort of convergence rate. And what does convergence mean? Well, it basically means that if we pick enough time points within our interval, the sort of error we're making becomes smaller. So that means basically we can increase the amount of compute we use to get better estimates. And so what's this stability thing? So one classical way of sort of formalizing this notion is astability. And what do? Well, you take some linear test equation, y dot of t equals h of y, and then it might have some initial condition. Now, the definition of astability then is if the solution actually dies, then also the solution of your solver should die. And by dying, I mean going to zero, as the number of time steps tends to infinity. And you typically consider this on a uniform grid. Or well, you do consider this on a uniform grid. Now, I'm not going to sort of go into details and sort of derive a bunch of things, but we do get these sorts of analysis for free in our case, because we're using these linear Gaussian state space models, and these are pretty well studied from the perspective of systems theory and control theory and so on. And so the result is actually that if our matrices A and B in our state space model are controllable, which again just means that I can replace the Wiener process with some other input to just steer the state to wherever I want, then, well, the solver is astable if and only if this transition matrix in our transition density, which is now a constant because we're on a uniform grid, and this observation matrix, which is also constant, well, if that pair is detectable. And detectability is kind of a generalization of this notion of observability, which meant I could reconstruct it straight from the outputs y to the more general case where, okay, suppose the bits of the states I can't reconstruct just die to zero all on their own, then we say it's detectable. So the things we can't reconstruct are just going to die after a while, so we can still kind of reconstruct them because we know they're going to be zero after a while, roughly speaking. Now, controllability is just a property of the prior. And so I have, in fact, designed our class of priors so that they are controllable. So what's left is detectability, and that is to some extent determined by the method. So if I use a zero for the method, it's not going to be detectable in general, for instance. Now, interestingly, this detectability condition does not depend on whether this H matrix in our test problem is Hurwitz or not. And Hurwitz basically just means the matrix is such that the solution is asymptotically stable, that is, or well, exponentially as opposed to zero. And so you can get kind of funny results. So we do have stability over solvers, but they're perhaps a bit too stable. So if we try to compute the exponential function, which is governed by this differential equation, then here I'm using an integrated Wiener process of orders new 1 through nu equals 4. And so in the solid line, I plot the estimates we get from the filter, so the forward recursion. So we see that it sort of tries to increase exponentially, but after a while it just gives up and flatlines. And then once you do the smoothing recursion, it just stays flat. But you also see that as you increase the order, it becomes more eager to grow before it finally gives up. But I can increase the order to any sort of number, and then it's still gonna die after a while. So I don't know what people think about this, but in a sense, I'm not sure I care too much about it, because I don't know if people solve things that just explode anyway. So in that sense, I'm not too worried about it. So that's stability. We also have this problem of convergence, as I mentioned. Excuse me. Now, I'm going to sketch this really loosely. But the point is that our map estimate gives us a function x hat, which sort of encodes an estimate of the solution y hat, which is an estimate of the solution and all of its derivatives. And we can sort of write y hat of t as equal to, well, y naught should be safe. I used safe as the initial condition earlier, I guess. And then you do plus, well, an integral of its derivative from 0 to t. So this is just differentiating and then integrating again, basically. And now I can add and remove the vector field v evaluated at y hat. So that I get this bit. And this is kind of the integral formulation of the differential equation. But I also get some sort of residual bit, so an integral from 0 to t of this z of y hat. And z of y hat, of course, that just needs to be this derivative of y hat minus v at y hat. So that this last line here actually equals the y hat. Now I'm going to call delta the sort of maximal length between my grid points. I say zeros here, because if y hat is the map estimate, then by definition this guy is 0 at the grid points. So this said y hat of t is a function which is 0 on a lot of places throughout our domain. And we can sort of add grid points to make it 0 at even more points. And so in some sense, it's starting to look like we might actually have something that could converge. But the question is how quickly. Well, okay, so there is this sort of result that if, so suppose the component of this Z, I call them Zi, are in fact Sobolev functions of smoothness nu, then from Arkangeli et al. 2007 we get this kind of result. So we get that the Sobolev semi-norm M with sort of exponent Q, I guess you call it, is then bounded by, well, this sort of delta to the power of a bunch of things times the semi-norm of order nu, and then obviously these two, which is the sort of Hilbert thing. So HMQ is just the LQ norm of the nth derivative. And I'm gonna also kind of need another thing, which is, I call it norm domination here, which basically means that the Sobolev norm of my estimate in terms of smoothness nu plus 1 is smaller than or equal to some constant that doesn't depend on the solution, times the Sobolev norm of smoothness nu plus 1 of the actual true solution. So if my solution lives in the solid space nu plus 1, then this actually tells us that we know the radius of a ball around the region within which our solution estimate exists a priori, and the radius does not depend on the on our estimator. So I'm also going to need a kind of Lipschitz property of this ZI. Yeah, so first I take the semi-norm of smoothness nu, and then that's of course smaller than the norm of smoothness nu. And now I can take minus Z at the true solution, because by definition the true solution evaluated at Z is 0 everywhere. And what I want is, well, this kind of Lipschitz property then, so that there is a constant that does not depend on our estimate, multiplied by the difference in some norms of smoothness nu plus 1 of estimate and solution. And of course, due to norm domination, that just means that this thing, I can just use triangle inequality here to get rid of the estimate, and then just replace C2 by C3 and have the sublet norm of the solution. Now, the convergence statement is kind of like so. So if our vector field is nu plus 1 smooth, so continuously differentiable nu plus 1 times, and we define this E as the sort of residual term in our solution estimate, we also need to assume that the unique solution exists up until some time point, which is after the interval we're considering solving on. So we consider solving on interval 0 to t. We want this solution to exist on that interval. Then we have some positive constant, C4, such that we can bound this guy in terms of a bunch of Sommel and semi-norms. I guess the most important one is the one here above, so the H0Q norm, which is just the LQ norm. It's then bounded by this delta to the power of nu, so we get a convergence rate of nu, and then this is just a constant. And this second one, yes, we can get convergence rates for our derivatives as well. So we're not only estimating the solution, in fact, we're also estimating the derivatives of the solution. That one might be useful in some applications. Who knows? Now, wait. Yeah, that's the result. Something went wrong. Okay. Yeah, no, something did not go wrong. Yeah, so what we need to assume is this, so that the vector field is in fact nu plus 1 smooth, and that the solution exists. And what I haven't done is establish that the true solution lies in this Sommel space of smoothness nu plus 1, or that the solution, or that our estimate actually lies in the same Sommel space. And I haven't established this guy either, which is the norm domination condition. But all of these things basically just follow from RKHS theory. It turns out that our prior actually has an RKHS that corresponds to, or is equivalent to this Sommel space. So the norms are equivalent and they have the same functions as well. Now the tricky bit here is this ZI, so this local Lipschitz condition. But it turns out that in the middle of a proof, as a sort of by the way, this guy valent, this guy's like, oh, this holds. So you do have that. And so basically most of the work is just like making sure that all the Sommel things work. Now, is the map estimate good? Well, only eventually. So here I solve, I think, a logistic ODE. And I have a really tiny initial condition. So that I want, so because essentially the logistic ODE is just a quadratic, so x times 1 minus x. So if the initial condition is 0, then a map estimate would be 0, or well, then the solution is 0 everywhere. And if it's almost 0, then the 0 function is very close to the sort of, it's a very good interpolant of our ODE data. And because the map estimate sort of corresponds to minimum norm interpolation, that just means that we kind of get biased towards this guy. So if I use 25 grid points, we see that we do get a map estimate that just dies. I can increase it to 35, it still kind of just dies. I can increase it to 46. It does something, but it still kind of dies. And then I increase it by 1 grid point, 47, just snaps to this S-curve, which is the solution. So there are some funky stuff here. So while we have good convergence rates, they only hold eventually, which is important to note. And it's not entirely clear how to figure out what eventually is before you try solving it. That's a bit of a drawback, but other than that, I think I'm basically done. So I did talk a bit about priors, and we've seen that the prior kind of determines can have a kind of significant effect on the behavior of the solver. And now there are some open problems. So I've only talked about sort of approximate filtering and map estimation. As far as I know, no one's been working on sort of figuring out how the actual sort of idealized Bayesian posterior of a problem behave. Well, as I mentioned, these Gaussian approximations probably need to be examined to figure out sort of, can we give any guarantees when they're reasonable, how many grid points do I need, and so on. And also, well, we've kind of used sort of standard method to approximate base rules in this case. Maybe we can do something smarter in the future. Maybe we can consider doing particle filters, which might be a good way to sort of examine the behavior of the posterior, at least empirically, not theoretically, but that's something that could be useful to do. But other than that, I think I'm kind of done. Yeah. So thanks for listening. Hopefully it wasn't too much of a drag.
Thanks very much, Filip. It's a very, very nice tutorial introduction to quantity numeric ODE solvers. Well, we've got plenty of time for questions, so can I open up for questions?
In the slide before this one, did you use the calibration routine that you outlined?
Yeah.
So this is actually fairly badly calibrated, right? It's not the estimate here if the true solution of this problem is the one you get in.
Yeah. Yeah, it's horrible.
Would you say this is an artifact of the prior, or where does it come from?
Well, I mean, the problem is you can't. I think you're going to have a hard time constructing a method that is guaranteed to be well calibrated for any experimental design. So, for instance, design a Bayesian quadrature method using one node that is well calibrated. I don't think you're going to do that in general.
So would this also cause problems for standard numerical methods?
Which bit, sorry?
So the standard numerical method would give you some idea of what its accuracy was, as well as the estimate, right? So do you think in this sort of scenario, a standard method would also underestimate its error?
I think the problem here is that this sort of solver structure is so different in standard methods because you just extrapolate in the future all the time. This is essentially due to the sort of minimum norm interpolation property over a map estimator. So if you do construct a solver with splines, then it's also going to suffer this thing because this is equivalent to splines basically.
My question is, the measurement covariance, is that positive, definite, or zero? Because I see one slide, you put zero for your measurement.
I'm trying to, here I did. So I put zero here, yes.
But there are two questions. First is that if it is zero, then it is not the canonical common filter, because common filter assumes the measurement noise is positive, definite, and how can you prove stability because it's not positive, definite?
Well, no, so the measurement, so this R is not positive definite, no. But my filtering covariance is also not going to be positive definite. But my prediction covariance is going to be positive definite. And that's typically how you prove stability of Kalman filters. Right? You first establish that
the covariance R is positive, definite?
No, in my case it's zero, so we just remove it. But the sort of equations are all the same.
The traditional proof of common filter assumes that the R is positive.
Yeah, the traditional proof of the common filter, but you don't need that.
Okay, so the second question is you talk about the smoothing, but if you want to, for example, you want to estimate the state of T, do you need to condition on the future measurements? Because I know your measurements can be constructed for any time.
Yeah.
But do you need to condition on the future measurements? And if you don't condition on the future measurements, but consider the filtering problem, what will happen?
Here I consider the filtering problem. So essentially, each point on, let's take this line so I don't have to reach so far. This corresponds to the actual a posteriori estimate used at this time point using all of the data up to that time point. So you can certainly do that. So for instance, if you're only interested in the sort of terminal value of your ODE, then you just need a filter and there's no backward recursion necessary.
And another question is that what's the relationship between the stability of the ODE solver and the stability of the common filter? Is that the same?
You mean for my ODE solvers or ODE solvers in general?
Your ODE solver.
Yeah, so this is just the classical, I'm not saying this, but this is just the classical exponential stability of Kalman filter result applied to my particular setting.
So this actually the same?
Yeah, so I just pick up the book by Anderson more optimal filtering, I go to the chapter on stability, and I go like, this is my thing.
Okay. And another question, so I'm curious about why you put the measurement noise to be zero, but instead of the transition
noise. If my transition noise is zero, then my model, okay, let's go here somewhere. So if my transition noise is zero, then my prior is just a polynomial of odd and new. And that is not sufficiently flexible to model ODE solutions. So I need the measurement noise to sort of be able to model any kind of integral.
Is there any possibility to put the error term on the measurement noise?
No. Because once your prior model is in polynomial land, you're going to stay in polynomial land after base rule. And if your solution is not close to a polynomial, you're not going to have a fun time.
posterior mean would coincide with the standard numerical method.
Yeah.
And so you could do this and you could recover like the Roland-Cutter family methods, for example. And I don't think they would necessarily fail on this exponential example in the same way that the method you presented did, right? So what has changed in the last few years that's giving you this extra stability?
So these things that reproduce Runge-Kutta method just do it over one step, right?
Oh, okay, so they would still...
So they would have to chain a bunch of solvers. So they would be in the land where they just approximate this flow map somewhere. Oh, it's very far back. Yeah. So I guess in a sense they're just approximating this guy and just chaining it together.
So they would also have this sort of excessive stability.
Well, no, I'm saying they wouldn't, because they're kind of building an extrapolate and they just iteratively.
Oh, okay.
So the problem here comes from the sort of considering the problem globally.
Right.
So we have one function rather than a series of extrapolates.
Okay.
Yeah.
So if you say that the problem comes from considering the function globally,
Yeah.
is that related to, so does it mostly appear for the map, or does it sequentially appear?
Well, I mean, the stability is for all the things.
Or maybe a different, so not on the stability, but on the other thing that you had, where you need exactly a certain number of points to snap to the true solution.
Yeah.
Is that also the case for not the map, but not for the...
I would guess. It was a while ago since I looked at this. I know you can have the cases where this sort of filter gives you a very nice estimate of the solution, but once you do smoothing, it just dies down, and that's kind of almost a map estimate. So that could happen. So in some cases, these sort of approximate Gaussian solvers, they're close to the true solution, but they're not close to the map estimate, and they might even be better than the map estimate because they are not fulfilling this minimum norm property that the map estimate does. But then, again, whether they are better at approximating the mode of the sort of true posterior is probably not true, so it's a problem of the prior, I would say.
Okay. There's no further questions, and let's thank Filip one more time.